Object detection has paved way to many interesting metrics for evaluation, and we will be discussing with around some of them in the next few slides. And the first one is intersection over union. So this is actually an interesting concept, and it's also called Jaccard similarity or Jaccard index, and it's also widely used with segmentation, image segmentation as well. And the idea here is we have an annotation which is done by a human, a bounding box drawn by a human, and the neural network is going to predict the coordinates of the bounding box as well. And after the training is done, the model will predict a bounding box and how similar is that to the annotation done by a human. So intersection over union is a matrix which could give some kind of measure of that similarity between the prediction of the model and the annotation done by the human. So it is if A and B are two sets. A is basically the prediction, let's say, the bounding box governed by the prediction, and B is the bounding box governed by the ground truth or the human annotation. Then what we are essentially doing is we'll find the intersection between the prediction and the annotation or the ground truth, and we divide that by the union. Okay, so what is common? That is a total overlap. Basically, the not even overlap, the superset, and you divide the overlapping region um, by that. Okay, so that's the idea. So it's pretty simple. Okay, so uh, pictorially it becomes very evident. So let's say the ground truth is shown in green. I have adapted this from the slides from Michigan University, so you can check the references for more details. And the prediction, let's say it's in the blue box here. When we say intersection over union, it is basically the intersect region, which is basically this orange shade, that is divided by the union, which includes basically this part and this part. So area under this observation. So of course we know that the area is length into breadth, and calculation is actually pretty simple. So you find basically the overlap, and you find the length and breadth of the overlap, and then you multiply, you get the area there. And similarly you kind of subtract the area, the bigger area basically from one of them, you get the union as well. So that's the idea, and code is given here adapted from the D2L .ai textbook. um, let's actually see various cases. Okay, so if the overlap is this much, we know that there is fair overlap, maybe 50%. That's what it's kind of showing here. So IOU score is 0.54, which is decent, not bad. And a slightly better is basically 0.71. We can say that this is much more overlap here. And then of course this is the ideal scenario. Of course 1 is very difficult to get, but anything above zero point 0.9, intersection over union of zero point 0.9 is actually a very good prediction. Okay, so that's the concept. So the idea is you find the prediction bounding box, you find the annotation bounding box, you find the intersection between them, you divide the intersection by the union. So that's basically the idea. Now this is basically used to evaluate the performance of the prediction in a very coarse sense, and it is also used to suppress multiple bounding boxes maybe around the neighborhood. Okay, so I'll tell maybe explain again with reference to the slides from Michigan University. I'll use the same set of slides. So let's say this is the prediction from an object detection model. So two dogs are predicted, and you can see we already know the problem. There will be multiple predictions around the same region of interest. So for example, here this particular dog is having two bounding box around it, and this particular dog has two bounding box around it, and the corresponding confidence score for the prediction is also displayed. So this is like probability that this prediction is a dog is 0.9 here, and zero point 0.8 the orange one, 0.7 for this yellowish orange, and 0.75 for the purple one. Now we can use the intersection over union cleverly here to suppress some of these boxes, and that process is known as non-maxima suppression. Okay, so whatever is kind of uh, very similar or having a very good IOU with respect to each other, we will only keep the highest of them. We will remove or suppress the lower ones. Okay, I'll explain with the example here. So the process is something like this. You select the highest scoring box irrespective of uh, the prediction probably or the class. You select the highest one. So in this case we only have dog, but let's select the highest one, which is this box, this particular box, which is zero point 0.9. So we'll select that, and then you kind of find the intersection over union for this box, the highest one, with all others. And if there is a very high value, that means they are very overlapping, right? For example, these two, the orange one and the blue ones, they are very much overlapping, so they are expected to have a very high value of intersection over union. So if that is the case, let's say above a threshold of zero point 0.7, we will kind of suppress the box with the slightly inferior classifier score. Okay, so we'll illustrate that. So let's take the first one. The highest one is zero point 0.9. So I'll take this blue box. Then I will do the intersection over union with the orange one, with the yellowish orange and the purple. And the values are kind of illustrative examples. So values are tentatively this. And this is very high. We know that they are very close. So a lot of overlap. And it's expected to be very high. Whereas the other two are far away from this blue one, right? So in that sense, this is basically this guy and this guy have very good overlap, and these two are not that. So it's actually evident from the score. So then what we are going to do is we will suppress the one which is having above a threshold, let's say 0.7, good overlap. So we'll suppress this orange guy. Okay, so that's the first step. So we'll remove that. And now the next one is, obviously this is done. So we have nothing overlapping with this now, because the IOU score for all others are lower than the threshold. So if another one was higher than the threshold, we would have suppressed that also. Okay, so this is done. Now next, the best score is 0.74, which is actually the purple one, or 0.75 rather, it's a purple one. And we will do the correlation with all. We don't need to consider this because that was already done. So we'll do with the orange one, which is coming to be 0.74, and again it's above the threshold, so we'll suppress that. Okay, so that's basically the idea. So that means actually you will kill this guy also. So the two bounding boxes which will remain are this guy and this guy, and that's kind of perfectly overlapping with our requirements. And the code for the same is pretty straightforward. I've taken from excellent the GitHub profile, GitHub codes by Aladdin. So you can actually go and see this. It's actually quite straightforward. You can actually see it will sort the boxes, and then you can see the sorting here. And then from the highest value, it goes in a kind of a while loop with IOU calculated with that particular box with all other boxes. And if it's above, the IOU is above a threshold, you suppress them, and then you go to the next highest one, and so on. Okay, so that's the idea. This will work well when you have maybe few objects, but consider an image like this and you want to put a bounding box on the crowd, then it's not really going to work that well. And by the way, this technique is known as non-maxima suppression, because you are going to kind of suppress whichever is having a very good maxima or a very good IOU score. You're going to kill all of them. Okay, but if you have something like this where too many boxes and too many overlaps, then probably we need a much better solution. And there are many approaches which are kind of sophisticated non-maxima suppression, so that you can actually do as a self study. Okay, last but not the least, so we discussed about the intersection over union, and then we also discussed about a clever use case for intersection over union, and that is to kind of suppress the overlapping predictions. And that's very useful because you are supposed to get multiple overlapping predictions or bounding boxes from the object detection algorithm, and using the IOU is a very clever way to kind of suppress that. And that process is known as non-maxima suppression, and that is kind of a post processing which is heavily used during the inference stage of all object detection models. Okay, and now we have discussed about all those aspects. Now we need to discuss about the evaluation metrics for any object detection model, and the most common one or most popular one is known as the mean average precision. So it's a very complicated idea, but it's actually an interesting idea as well. So it is actually the mean of average. So mean and average, you might be thinking, why it is actually the same name, but this mean is actually the mean of classes. Okay, because you have multiple classes, multiple objects are there, each belongs to a separate class. So this mean is across the classes. So for all the classes you are doing the mean, and for each of the classes you are doing an average precision. So that is very important. So mean across classes, and for each, so on what is that mean applied on? That is on the average precision, and this average precision is done per class. Okay, so you have a class and you calculating the precision values, and then you are kind of averaging that precision, that is for a particular class, and then you consider all the classes, so you have multiple average precisions, you do a mean across them. So that's why it's called mean average precision. So slightly complex terminology, but it makes sense. Okay, so let's dig deeper. So this is again, I mentioned it, so no need to repeat it. Average precision is estimated as the area under the precision recall curve. So basically the first step is you predict the bounding boxes, and then you need to calculate the precision and recall. Okay, we will define that very slowly, shortly, and this is also used in classification as well, but this is slightly different way it is getting used in object detection. So we'll define what is precision and recall, and then we will kind of use that to come up with mean average precision on a sample case. Precision is basically, this is standard, it's not object detection specific, but precision in general is total true positives by total of true positive and false positive. Okay, so this basically means all the predictions. True positive or false positive means it is more towards the predictions, nothing to do with the ground truth. So you can say that out of all the predictions, how many of them are true, that is precision. Correct. So total predictions, nothing to do with the ground truth, again I'm repeating that, that's this denominator, because all positives, whether it's true positive or false positive, will come to what is true positive and what is false positive very soon. But the sum of true positive and false positive is nothing but all the predictions. Okay, so out of all the predictions, how many of them are true? Okay, how many of them are true? So let me put it this way. That's why it's called precision, because how precise you are with the prediction. So I predict n number of times, out of that maybe k number of times it's correct, or it's true, it's actually correct. So that is the precision. Similarly, recall is true positives by true positive plus false negative. So this is interesting. This actually is ground truth. It is related to the ground truth, because all the annotations, out of all the annotations, how many of them are true? Because false negative is, maybe I'll explain true positive with all those things with example here. So true positive in the case of an object detection, considering an IOU score of 0.5 as threshold, it's important. Okay, so we have to choose an intersection over union threshold. So let's say it's 0.5, so it's very common. Okay, so 0.5 is our intersection over union. So the green one is, let's say, the ground truth, and the red one, or rather the green one is the prediction, this is the prediction, and this is the ground truth, which is annotation by human. Okay, so how much overlap is basically your IOU, right? I mean overlap by union, basically intersection by union. So this is very high because it's pretty close, and this is very low because it's way off. And this is an interesting case where you actually have no prediction, but you have a ground truth. So that is false negative. Okay, so let me now reiterate true positive, false positive, and false negative, and then we'll come back to precision and recall once more. So you have, if you have a very good overlap or very good IOU score, that means it is a true positive. Okay, so that means your prediction is correct and it is really there. So that's true positive, right? Your prediction is positive and it is truly there. So true positive. False positive means you are way off. The annotation is there, but your IOU score is very low, so you are not really predicting correct. Okay, so it's actually kind of false positive in that sense. Okay, so your prediction is really not correct in that sense. So that's exactly the scenario of false positive. And false negative means you are not predicting at all. Annotation is there, but you are not predicting, so that's false negative. So there is another concept, true negative, which we are not considering here for precision and recall. And true negative is basically something which is related to you predicting it, but that's not there at all. The ground truth is negative, but I think I made a mistake, small explanation mistake. Positive is respect to the uh, kind of prediction, and this false is kind of what you look at for the, sorry, positive is with respect to the ground truth, and false is, I think, yeah, maybe I'm confusing it. It's okay. So positive is prediction, negative is prediction. So you have predictions here, so it's positive. But if both the annotation and prediction are accurate, which in this case is overlap is perfect, you have true positive. If overlap is way off, that means you're predicting it wrong, that is false. Your prediction is false, so it's false positive. And here you are not even predicting, so it's false negative. Okay, so that with that concept, now if you come back to the precision and recall, so this true positive plus false positive is all related to prediction. It has nothing to do with this guy false negative. So it's all predictions. You have predictions, wherever you have predictions, you're counting that here. So how many are accurate predictions out of total predictions? How many are accurate predictions? That is basically the precision. And recall is basically, this is all the annotations, because true positive plus false negative, it's all annotations. You have two annotations here, and that's actually kind of uh, basically considered for the recall. So out of all annotations, how many of them you're predicting correctly? So it's more towards the accuracy related aspect of your prediction, correct? Because how accurate you are, the annotation is the ground truth, and how closer you are to the annotation on a number of cases. Okay, so that's the exact scenario. So this is the recall and precision are not calculated per image, but for all the predictions together. Okay, that's very important to know, because here I'm only showing like one ground truth and three different predictions here. Okay, so each one of them you can classify as true positive, false positive, and false negative. But when you want to calculate precision and recall, you may need to have more number of example cases. Okay, let's come to that. Okay, so I'll take an illustrative example now. So let me remove all this. So we'll take an illustrative example. So let's take, again, I adapted this from Aladdin's YouTube channel. So you can find the link here and the code to the object detection metrics nicely done by him on this link. So please refer to that. Okay, so if you see here, three separate images and the predictions are shown in red. So the red color is prediction. Let me write it here. So red is prediction and green is basically your ground truth. So how many ground truths are here? So 1, 2, 3, 4. So 4 ground truth is here. So for recall, your denominator should be 4, right? Because recall tells you how many of the ground truths are predicted correctly. And for precision, you need to be counting the number of predictions. So in this case, we have 1, 2, 3, 4, 5, 6, 7 red boxes all through. So 7 predictions. So the denominator will be 7 for calculation of precision. Okay, so let's go through. So for the first image, now going by the score, let's calculate it as true positive and false positive. It's a good exercise. Again, I'm using IOU of 0.5 as the threshold. So image 1, this is the image, and you have the first one, basically 0.3, which is this guy. And of course, we know that it is way off than the so here only I'm doing false positive, true positive. Um, so this is false positive, of course, because you have annotation, so it's not false negative, it's way off, so it's false positive. So false positive, if there is no annotation, then it would have been like maybe false negative, because sorry, true negative rather. False negative is like annotation is there, but you're not predicting at all. So here you are having annotation and you're having prediction, so it should be either true positive or false positive. since this guy is way off, it's false positive. Its IOU score is very low, it's below 0.5. So this is IOU score. By the way, this is the IOU score mentioned here. So you have false positive, this one. 0.6 is this, which is above the I mean the cutoff is basically 0.5, so you don't have much of overlap here, so it's false positive. And this is actually the classification score kind. Okay, so that is something which you can um, at this point it's not useful, but when you come to the next level or next stage of mean average precision, it makes sense, so you can ignore at this point. But this is having, you can see, no overlap, so it is false positive. This one is decent overlap, but not half of them is overlapped, so it's below 0.5, so it's false positive again. This one is having perfect overlap. Okay, so it's true positive. So don't get lost in this. This is not IOU score, this is the classification score. IOU score is just visually seeing and whether there is good overlap or not. So this one no, this one no, this one yes. So that's what we are doing. So this is true positive, others are false positive and false positive. Here this decent overlap, so this is definitely true positive. And this image, three of them again, this one no, so that's false positive. This one, even though the score is saying very high, but it's not, so it's not considered false positive. This one is true positive because it's having good decent overlap. Okay, so this is yes. So that is the thing, so this is also yes. And now the next step in the case of, so what we are doing here is actually the mean average precision calculation. Okay, so average precision is explained in this chart. So we have the images, we have the predictions, we have the ground truth. Based on the prediction and the ground truth IOU score, I can make it or mark it like true positive or false positive. So that's what we have done so far. Now next step is, we are doing it for, again that is important, we are doing it for only one class here, and that is for the dog class. Okay, so you, what we need to now do is we need to sort the classification score and sort in the descending order, the highest one at the top, and we need to actually make that table. Okay, so I think this we discussed now. So the total ground truth detection is the annotation, so we have four of them, so that's why this is four. And we have total seven red predictions, so that's seven. So this affects recall, this affects precision, so please remember that. Okay, now what I'm going to do is I will sort this by the classification score, and then we'll calculate the precision and recall one by one. So I have the entire table here, but we will do it one by one. Let's start with this. Okay, so the sorting is done by the score, the classification score for classifying the image as dog. So that's basically this. Image name is here for reference, but not useful at this point. So score is what you're looking at, and then of course I adapted the true positive whatever values coming from this to here. 0.9, you see here it's true positive, so it's there. So what we are having is, we are going to do kind of precision one after the other. So one prediction after the other we are going to consider. So recall, we already know there are four ground truth. So out of four ground truth, we already have one true positive. So 1 by 4 is the recall. Remember, recall is true positive by total. I think it's basically all predictions we can say. Sorry, all GT ground truth. This is recall. I'll write this so that it's easy. The other one is true with all predictions. So in this case, this is 4 and all prediction. In this case, it is 7. So denominators are fixed already. So you can see it here, it's already kind of fixed for recall, but this one is gradually increasing, but it will increase up to 7 because we are considering one case at a time. Okay, so you have one recall already. One is basically successful out of the four ground truth. One is detected. So 0.9, which is this one, this is already correct. Now going to the next, which is this 0.8, but it is a false positive. So that means the total predictions have increased to 2, but the true positive remain at 1, which is this. So that's why it's 1 by 2. And true positive is again 1, so it is 1 by 4 here. So total basically you are kind of cumulatively doing it. And now next one, 0.7, that is also true positive, which is actually this one. So it's true positive. So we have one more true positive, so you increase the numerator 2 in both cases by 2. So this is 2 by 3 because the number of predictions have become 3 now. So 2 by 3, and the ground truth is already 4. So 2 by 4. And similarly, you keep on. Maybe one more case we'll explain. Point 6 is false positive. So that means you number of cases increase to 4, but true positives remain at 2 because only 1, 2, and you have 1. So total is 4 predictions. Out of that, only 2 is correct. So 2 by 4. Similarly, 2 true positives and total 4 annotations. So that is run. So you can do for the remaining. Now if I plot the precision against recall curve, so you have this. So these are the points. So 0, I'll just assume it to be 1. At this particular value, somewhere around here, which is 0.25, it is going to sorry, it is 1 already, and at the same value it dropped down to 0.5. So basically this point is this point, and this point is this point. Okay, so you plotted it. Let me remove all the ink now. Okay, so what you're going to see is a curve like this, and the mean precision is basically the area under this curve. So if I take the area under this curve, you get somewhere around 0.53, and that is basically the average precision for this particular class, which is the dog class. So that is the average precision. So again, I reiterate the steps here. You find individual cases, true positive, false positive, then you sort them by the classification score, and then you do the cumulative precision and recall. Okay, so only difference is recall, you already know the total ground truth, so you do that, but true positive, false positive, you only know as you kind of move forward, right? So that's the case. So this is the kind of uh, chart that you get, and then you have a curve, precision recall curve, and then if you take the area under that curve, it gives you the average precision. So you got the AP. Now there is a small guy M left. So what you need to do is, this is a dog class. Let's say there is a cat class here. So you need to do the AP for the cat class again. So you have the AP for the dog, which is this. We have, let's say, similarly calculated the AP for the cat, and now mean AP, if only 2 class problem, then it is basically AP dog plus AP cat, basically the mean. That's all. So if you have n classes, so you have n classes, so you need to do the AP calculation, the average precision calculation for each of the n classes, then you take the average of that. So that is known as mean average precision. So this is a very, very important evaluation metrics in object detection, and it's very popular as well. And very interesting part is, they call in this particular case MAP at 0.5. What is this 0.5? Any guess? You can pause the video and just have a guess here. Okay, so the answer is, this 0.5 is coming from the IOU threshold that you choose. So you can change the IOU threshold, then the entire curve will change. So let's say you change it to 0.2, you change it to 0.9. So whatever threshold that you are choosing, that is important, and you need to mention your MAP with respect to that. So MAP at 0.9 means I have chosen IOU of, or intersection over union score of 0.9 as the threshold for calculating the average precision. So that is the meaning of it. So if you work in object detection space, you may have to vary the IOU from, let's say, 0.05 to 0.95 in steps of 0.05. So that is something, and then you take an average. So average of this average. So MAP is already an average of average. You take one more average over this range of IOU. Okay, so that is very important as well. Okay, so I hope you understood this. This is a very fundamental concept which is heavily used in all the object detection models.